Hey everyone, welcome back to another week of learning a little bit differently through our flipped lessons. So today and next week we're going to talk about energy. This week we'll have a flipped lesson, and next week we'll have a flipped lesson and an explanation of our activity. This week we're going to be doing a little bit more math, so you might want to pull out your calculator and make sure during this time that you're taking notes, you're pausing the video, you're going ahead, really whatever you need to do to learn best. So if you took biology or chemistry, you probably have already heard of energy. Energy is the capacity to do work. Now, what does this really mean? This means that something has a force and it's going over some distance. Work is a topic associated with energy, which we won't get to during this time, but if you take AP Physics, you'll see it again. Energy can be in multiple forms, such as potential energy and kinetic energy, which we'll talk about. And then in chemistry, you may also see thermal energy. We measure this in joules, which is actually a shortened version for a much, much longer different variables. And like I said before, energy is a really important part of all the sciences, and you should have already seen it in biology, and maybe you've seen it or going to see it eventually in chemistry. And that's when we talk also about potential energy, but also thermal energy. So these are the two different types of energies that we're going to focus on in this class. Potential energy is the energy when something has height. Okay, so this U also stands for potential energy. So I sometimes will write PE, but U is more of the generally accepted way to write potential energy. And to get this equation, we have M, which is mass. And as a reminder, this is in kilograms. We have gravity, and we're just going to round for this to 10 meters per second squared. And then our height is in meters. Cool. All we do is multiply them together. It's a pretty straightforward equation. Our next one is kinetic energy. And this is the energy when something is moving. So we also have, for this one, K or KE. Very similarly, we have mass. So mass is a really important part of energy. It is in all energy equations. And that V stands for velocity. Like we've learned a long time ago, that's in meters per second. Okay. Now, remember, this is V squared. So the V is the only part that's squared. That's one really big mistake I see as we go through this. So let's start applying these equations. Before we start doing some equations, we're just going to look at this roller coaster. So roller coasters are some of the best ways to explain energy. Now you'll see at each of these points, this object has potential energy because it has height. Now, if we look at D down here, which is a height equals 0, I don't have any potential energy. However, I have all kinetic energy, and we're going to see what that means a little bit later. So let's do some practice. So this problem is a 30 kilogram person. So my mass is 30 kilograms, stands on top of a building which is 40 meters tall. What is the potential energy of the person? So we know that I'm going to use my equation, mgh. And remember, for gravity, because these numbers end up being so large, a joule is a very, very small unit. We are going to just round it to 10. It makes life a lot easier. So if I plug this in for my answer, I'm going to get 12,000 joules. So make sure that you are actually doing all the math written out for this and multiplying it so that you can double check your own answers. All right, let's try some kinetic energy problems. Kinetic energy. So a 1 kilogram ball drops. So I'll write down my mass is 1 kilograms. And when it drops, it has a velocity of 2 meters per second. So to ask, what is the kinetic energy of the ball? So I know I need to use my kinetic energy equation. So I'm going to write this one out to make sure that we do it correctly. So I have 1/2 times my mass, and then velocity squared. Like I said, velocity is the only thing that's squared. And that squared does not change the unit as well. So if I just reduce this a little bit, I'm going to get 2 joules. So one thing that you should be able to see through this is as my mass gets smaller, so does my energy. So at this point, you should start feeling comfortable using these equations. Now it's time to focus on the really big part of energy, which is our conservation of energy. The conservation of energy, very similar to the conservation of momentum from the last 2 weeks, is that the total energy stays constant in the system. So at the start, if I have 100 joules throughout the whole thing, no matter what, my total is going to always be 100 joules. Now, it can transfer into different types of energy. So it can start with potential, transfer to kinetic, transfer back to some potential, but no matter what, it's always equal to the total. Now, this second statement I have, and it says this total energy at the beginning of a situation is typically what our total energy is. Not all the time, but in our examples, the total energy will be the first thing that we find. And often it's mostly potential energy, not always, but in our examples, typically it'll be that starting potential energy. So here's a visual example of this. If I have this roller coaster, at the very top, if I have a kinetic energy equals 0, this means I have no velocity, okay? And maybe I figure out that my potential energy is 100 joules, okay? So then it can transfer. So at this point, I have height, so I have to have potential energy, but also I have kinetic energy. Why? My total is always equal to that 100 joules. Now, as this moves down, I see that my potential energy is 0 because my height equals 0, and all that total energy is now in kinetic energy, and my total is still 100 joules. We can see that here, my total is still 100 joules. So in our next example, we're going to use potential energy to figure out the total kinetic energy at those different points. We're not going to get into how to figure out the velocity. We're just going to kind of stick with our basis and really big part of this, which is our conservation of energy and the total energy. So if you don't have your calculator, get it out. I'm going to go through kind of how to do these problems so that next week when you work on your project, you will understand how to do all of it. So let's start looking at how we apply the conservation of energy. So for this problem, we are going to look for the potential energy at each point, what the total energy in the system is, and what is the kinetic energy at each point. So before we get started, it's always a great idea for these problems that we organize our potential and kinetic energy. It's really going to help us think about what is actually going on in each of these situations, okay? So our first part, we ask for the potential energy at point A, okay? And I'm going to show the example for the math at the beginning, and after that, you can take some time to plug things in on your own. So for A, for my potential energy, I have mass times gravity times height. My mass for all of this is 1,000 times 10 for gravity times 50 for my height. So I'm going to get my potential energy to be 500,000 joules, okay? And what's cool is, guess what? This is at the top at rest. This is also my total energy the whole time. Now, if I think about this, if it's at the top and it's at rest, that means my kinetic energy is 0, okay? So that at rest at the beginning is key to us. Now let's go to part B. Part B says that my height is 25 meters. So for my potential energy, same thing, 1,000 times 10 times 25 joules. And that's going to give me 250,000 joules. Now, I also need to figure out my kinetic energy. How do I do that? I'm going to take my total energy and then subtract my potential energy. So that's going to look like my 500,000 joules minus my 250,000 joules, which is going to give me also 250,000 joules. So this is a time where we see both potential energy and both kinetic energy. Another really big misconception that I see is that we think we can only have potential and only have kinetic. That's not true. We can have height and movement at the same time. For part C, we can see the height is 0. So this means I have 0 potential energy. And that means my kinetic energy has to equal 500,000. Why? Because that's, once again, my total amount of energy in the system. All right, at part D, I have a height of 30 meters, and if I multiply that out, I'm going to get 300,000 joules. To get my kinetic energy, once again, I take my total minus my potential energy, which in this case will give me 200,000 joules. So a big part of this is that we are seeing the transfer from one type of energy to the next one. Okay, so total energy is our focus. Now after this, we could use our equations to figure out the velocity for the kinetic energy using our equation. We won't worry about that this week, but you are free to do that on your own. Finally, before we leave, last year, the way we remember joules is joules, not joules. That's my joke for the day. Awesome. Well, there are some follow-up questions now, and then there's a simulation and some practice problems. Remember to write out all your work, take your time, and always come back for your flipped lesson if you're not sure.